everyone, and welcome to Pint of Science, coming live to you from the City of Lincoln. My name's Kay Ritchie, and I'm the local Lincoln City coordinator for Pint of Science, and I'm going to be our host for today's show and our other shows on Tuesday and on Thursday. So we've got lots of opportunities for you to get in touch with us, and you can do that by typing into the comments underneath the YouTube video. So we'll be able to bring your comments up on the screen and have a little chat with you that way. So if you'd like to tell us where you're joining us from and perhaps what you're drinking, that'd be lovely. We'd like to know. And you can use that chat function in the comments underneath the YouTube channel to ask questions of our speakers. So what we're going to do today is have two talks from Jose Gonzalez-Rodriguez and Bonaventura Bino Mayolo. And in between each of their talks, there will be opportunities for you to ask questions, and we'll also have a chat about our creative reactions, which are our science-inspired artworks. While I'm waiting to see where you're joining us from in the chat, I'd like to take this opportunity to give a big shout out to my colleague and friend, Dr. Tessa Flack, who's operating everything in the background and producing today's show to make sure everything runs smoothly. So if we've got some answers from people, I'd love to know where you're joining us from. Let's see what people have to say. Erica joining us from Brazil. Wow, that's far away from Lincoln in the East Midlands of England. Welcome. And you're from Edinburgh. I'm sorry, I can't pronounce your name, but Edinburgh is a fantastic city. You can tell by my accent that I'm a little bit biased there. Switzerland. Wow, this is fantastic. I really didn't think we'd get so many people from all over the place. And Rebecca's joining us from West Yorkshire. Great, Rebecca. We're going to be talking about you a little later, I think. And Peter from Norwich. Hi, Peter. Thanks for joining us. So as I said before, you can use that comments function to ask some questions of our speakers. And you can also interact with Pint of Science on social media using @Pint of Science and the hashtag #Pint21. So without further ado, I'd like to welcome our first speaker, Jose Gonzalez-Rodriguez from the School of Chemistry at the University of Lincoln. Hi, Jose, welcome. How are you today?
Yeah, not bad, thank you.
Good, excellent. Now you can see I'm wearing my Pint of Science t-shirt, but you've got a pretty topical t-shirt. Can we have a look?
I have my heavy metals one, so.
Oh, that's awesome. Thank you, Jose. Okay, well, I'll just leave it over to you then to tell us all about recycling metals.
Okay, so thank you for hosting me. I'm going to talk about the recycling of bioavailable metals, as you can see on my title. And before I say anything else, I'm going to give you basically a little bit of introduction with that little video. So I'll shush.
Earth is the only planet in the known universe where life is thriving. Preserving life, our environment, and the balance in our atmospheric phenomena are key for our survival as species, but also to maintain peace and economic growth. Our lifestyle is frantic. We have conquered every corner of the planet, and we keep transforming it. Our industrial development has made it possible for us to live a comfortable life, expanding our lifespan and making it possible for us to explore beyond our planet and develop our culture. To keep this expansion, and to maintain our lifestyle, we need resources. We look for them everywhere. We mine the Earth's surface, but also we have gone underwater to obtain these valuable resources to meet our industrial needs. However, our development is altering our ecosystem, and in the process, we produce huge amount of residues that we do not know how to eliminate or recycle. Some of this waste still contains valuable components that are very scarce. Despite its value, we do not use them because we do not have the technology or the know-how to bring them back into our industries. Some of these materials are difficult to recycle, and they are dispersed in our waste. However, scientists at the University of Lincoln, led by Dr. Jose Gonzalez-Rodriguez, in collaboration with an engineering company, GSA Environmental, have developed ways to recycle them using smart materials designed to trap them. These smart materials represents a step forward to help recycling many of these valuable components, and a step forward in the right direction, towards a brighter and cleaner future.
So, yeah, you're now a little bit more aware of the problem. As you can see on my screen and your screen now, so actually you know that we basically are producing waste. We not just because as a consumer basically we throw what we don't need, but also because, as we said before, we are actually needing resources and we mine the earth. And it's funny because when you look at statistics, that they give you a little bit of a good hint of what is the size of the problem. So if you take into account just the European Union, 2018, 74% of the waste we generated in the EU actually is mineral waste. So some sort of concrete material or even rock, or that is basically 74% of 5.2 tons, 5,200 kilos per inhabitant in Europe. So another part is if you look at the electronics we generate. I mean, if you think that humanity is expected to produce 120 million tons of electronic waste by 2050, I mean, now we produce 50 million tons. So again, it's shocking how much of this waste we are generating. So a little bit of, I mean, just a little bit more of statistics to put things in context. You look at the 74% I was talking before, mining, construction, basically are the main sectors that actually influence that production of waste. And if you look at us, households, 8.2%. So actually, we are not, our house is actually polluting. Is basically, we are producing waste, but our industries actually also produce waste. So sounds very negative, but actually I don't want to be negative. I want to be positive. Why? Because if you look at the trend, and that's what you have on the screen now, from 2004 to basically 2018, that's the statistics we have at the moment. Actually, there is a trend in dropping the amount of waste we are producing. Not in everything. I mean, we still consume a lot of water, and that is a problem for the future generations. We are hungry of water, but that's a different talk. But yeah, you see that we are actually not bad in terms of reducing the amount of waste we are generating. But still, basically, there is, I mean, if you look again at the statistics for the European Union, 2018, we were recycling more or less 55% of everything that we were producing, but still 45% that we don't recycle. And that 45% ends in landfills or incinerated or disposed in any other way that sometimes are illegal. So just let's go to what is the value in the waste we generate, because that's the title of my talk, is let's waste our rubbish. So if you look at electronic waste, I mean, mobile phones, I mean, we have plenty of them. I mean, many of us basically have 2 or 3, depending on and then sometimes they end in a drawer and nobody knows basically they stay there forever, or we basically throw them. But actually, there is 100 times more gold in 1,000 kilos of electronic waste that you can find in 1,000 kilos of basically gold ore, the mineral. So actually, that is shocking, because we could actually mine that resource that is still there. So again, let's put numbers and money into this electronic waste. So the metals contained in this electronic waste are worth $62 billion. I mean, that is 3 times the annual production of all the silver mines in the world. So that tells you that there is some resource there we could actually, or we need to exploit. Then, if you look at the amount we produce, I mean, I'm going to give figures from the UK. In 2016, our electronic waste generation was 25 kilos of electronic waste. That's shocking. I mean, especially if you compare with the average of the world, which is basically 6 kilos. So obviously, we are a hungry nation in terms of resources for electronic components. Not that bad, because if you look at actually our recycling capabilities, I mean, and looking to the UK in the context of Europe, actually 67% of that electronic waste is actually recycled. And then you can see how other countries compare to what the UK is doing at the moment. So the other part I'm going to actually talk, because gold, silver, I mean, those are typical metals people actually find valuable. But another elements that are very important for us at the moment are rare earths, and some of you may know, but others may not. So actually, typical thing we do when we don't know something, hey Google. So actually, if you type why rare earths are important, they will tell you what rare earths are. So they are basically elements that are important for high-tech devices, but also for defense and clean energy production. So other metals that are also interesting we are interested in is especially one, rhenium. Again, hey Google, why is the element rhenium so important? And Google will come back to you to say rhenium is a very resilient material. It's actually used to produce superalloys that are going to be so critical for the production of basically materials that are going to be in turbines or basically high demand conditions, high pressure, high temperature. So they look pretty because, I mean, if you look at the way they look like, I mean, rhenium, yttrium, scandium, basically they are rare earths, and they are actually quite difficult to extract. Why? Because as you can see on a screen in the red part, they are actually extracted from subproducts or tails of other metals. So actually the concentration of those minerals in the ore is going to be very, very small. And that's why we need to find ways to actually do it in a way that it could be actually productive. That's where we come into this equation. That's where the people here in Lincoln, we have been playing with computers and smart materials. And what we've been doing is designing these materials to trap or specifically basically enclose yttrium, rhenium, other components. So, for example, one part of our research was actually getting those scrap metals that you can see on the screen, and that is actually that metal is CMS64, which is a superalloy that you can use in turbines of planes or basically other turbines, and we dissolve them. But then you need to extract the rhenium. The rhenium is the real valuable metal. I mean, just to give you an idea, a kilo of rhenium, I know it's a little bit cheaper, but not a long time ago was 10,000 pounds per kilo. So actually it's more valuable than gold. So what we did is creating these materials that you can see on a screen. And these materials basically are synthesized according to what the computer models that we generate basically tells us we should use. And by doing that, we are going to actually selectively trap in rhenium. We have designed some materials for scandium, for yttrium, and now basically we are basically ready to exploit them and try to make them into industry, so industry can use them. And then we can, by doing this, we can stop mining the earth and start mining our rubbish. So that's all from me, sorry. And thank you for listening. And if you have any questions, I'm going to be very happy to answer any questions you may have. Thank you very much.
Brilliant. Thank you so much, Jose. I had no idea that my drawer full of sort of old mobile phones and bits of electronic equipment could actually be my road to future riches. So it's really interesting.
Yeah.
Well, hopefully we'll get some questions from our listeners and our viewers, but I'd like to kick things off, if I can be selfish, and ask a question of my own. Your techniques for trapping the elements, is that the kind of thing that we could see scaled up to our local recycling plants, or does that have to be a sort of quite specialist production site that would use those techniques?
I mean, the technology itself can be tailored to any metals that you want. I mean, so if we go to the recycling plant and then they have, for example, any valuables or any elements that we want to trap, the only thing we need to know is what is the chemical form. And then we can actually get that chemical form into our computer, and then we can design these materials to trap those. So that's the way it's working. So in all fairness, basically, we can trap almost anything. But again, I'm a little bit, not almost anything, but nearly.
Okay, so in theory, then we could see that being used at the local recycling plants in the future.
Sorry, could you repeat?
Yeah, sorry. So we might be able to see that sort of technology being used at our local recycling plants in future.
I mean, to be honest, there are companies already using this technology in New Zealand, basically in Sweden. So it's something that is coming. So we're just basically using the technology to target specific materials that might be high tech or maybe strategic to governments or basically,
Okay, brilliant. So we've got some questions here. Paul Elliott is asking, how do you think we can encourage governments to invest more in this important area of research?
I think that the strategic nature of these materials is actually making governments to invest. I mean, if you look at yttrium or scandium, they are very localized in China, or some mines are in Brazil. When you go to actually you look at the importance of these materials to actually design engines that are going to withstand high pressures, high temperature, governments will be more prone to actually recycle what we have. So I know that some companies actually are not throwing these engines away. They're actually just keeping them till the technology allows them to recycle these metals in a proper way. So
that's very future forward. That's excellent. Yeah. Okay, Carlos is asking, that's really cool. Well, that's a comment, but I think that's really cool as well, Carlos. I'm in agreement. So what are the requirements that you look for in MD? Is that machine design?
It's molecular dynamics.
Molecular dynamics, there you go. See, this is why you're the expert and I'm not. So what are the requirements that you look for in molecular dynamics to design those trapping compounds?
It's basically what we are trying to do is create the environment. And I mean, we do these calculations in a very simplistic way. So we don't try to use, when you do these calculations, you can use solvent. We do it in vacuum. And we try to actually use computers in a way that screen the best materials or the best raw materials for these polymers, these basically smart materials. But obviously, we as a chemist, we actually look at the chemistry and the best synthetic route. So that's the way we do it, really.
Okay, brilliant. I hope that answers Carlos's question. And Patrick's asking, are rare earths infinitely recyclable, or do they diminish over time?
Rare earths could be technically the atoms or the elements are not going to die out. So actually, that is the way we need to do it. If you look, rhenium is not a rare earth, but it's very valuable. We only have 10,000 tons in the planet. In the moment that's gone, then we cannot basically produce high performance engines. So how are we going to have more jets? How are we going to have rockets that are going to go to Mars and do all these things we want to do? Until basically we start mining the asteroids, but then I don't think I will see that happening. We need to actually recycle what we have in this planet. So technically, yes, we could recycle again and again. That's what the concept of circular economy is about, is we don't throw anything away. We actually create a cycle where I use, I recycle, I basically put back. And to be honest, it's the nice concept where we can take something from nature and we can give it back so we can reuse it again and again.
Yeah, brilliant. Okay, I think we've got time for maybe one more question if we have another question. Excellent. So how much cheaper is the recovery process compared to the current mining process?
That is a very good question, because basically in industry, everything is driven by economics. So for example, for rhenium, because it's so expensive, then yes, you could actually get this profitable, and then you can actually use it. For other elements, we depend very much on the market. So let's say that vanadium is a very clear example. We could actually design a material for vanadium. It could be profitable basically now, but by the time we design the material, we can actually implement the industrial application. If the price drops, it might not be viable, and that happens with many things. So actually, we need to study metal by metal and element by element to actually see which ones are best for this technology.
Okay, brilliant. Well, thank you very much, Jose, and thank you everyone for asking your questions. So